Okay, I promised you another graphing problem in this lesson, but one that leads to a very powerful theorem in calculus. So let's first look at the things we want to graph. Those two things right there. They look simple enough, but the problem is going to come when we ask this question: what's the limit of each of them as x goes to infinity? What happens? If we were to graph them, we could graph each one of these things separately, and of course we notice that y equal x looks like this. E to the x looks like that, and ln of x looks like that. So we notice that as x gets big, this thing is getting big faster than this, and x here is getting big faster than the ln of x. Agreed? But just the fact that they're getting big faster doesn't give us any definitive information. In particular, if we look at x and 3x, then we notice that this one is obviously getting bigger than this. But this particular one we can figure out, right? As x goes to infinity, we can just divide through by the x's, and the answer is 3. So there's the answer just algebraically. The way we can get it graphically is by realizing that whatever distance this is, whatever height this distance is, this height is always going to be exactly 3 times as big. So as they go off to infinity, the ratio of this height to this height stays the same. It stays 3. And so even though they're both getting big, the ratio at which they're getting big is equal to 3. Now, as soon as I talk about the rate at which they're getting big, notice the rate has something to do with the derivative. So, for example, if I were just to take the derivative of each of these things, the derivative of the top is 3, the derivative of the bottom is 1. I guess I probably shouldn't have erased that so fast. And so that tells us that the rate of increase of this to this always stays 3 to 1. So that's very much connected to the fact that that ratio is equal to 3. So let's use that same idea over here. If we look at x over e to the x, notice that x always grows at a steady rate. Slope is 1. Whereas e to the x grows at a continuingly increasing rate. Right? If we were to take the derivatives of each one of these, we'd get 1 on top and e to the x on the bottom. And so just looking at their derivatives, we see that the rate at which this one is increasing is growing much faster than the rate at which this one is increasing. And that leads us to a theorem. I haven't proved it. All I've done is just kind of given you a reasonable reason to understand it as being true, to believe it, that as these things go off to infinity, we look at the rate at which they go off to infinity. That is, we look at their derivatives. And again, the derivative of x is 1. The derivative of the bottom is e to the x. And now, as x goes to infinity, 1 over e to the x, as x gets big, goes to 0. And that's the idea behind Hopital's rule. Basically just says that as two things are going to infinity, If they both go to infinity, then we look at the rates at which they go to infinity, and the rates are going to tell us what happens to the ratio of those two things. If we do the same thing here, notice they're both going to infinity. I like to put a little LR to stand for L'Hopital's rule. It says that since they're both going to infinity, L'Hopital's rule says we can look at the derivatives of each one and that goes to 0 because the rate at which this is getting big is so much slower than the rate at which this is getting big. So that's L'Hopital's rule, and we can apply it not only to things like that, we can apply it, for example, to something like this. As x goes to infinity, they both go to infinity, so we can use L'Hopital's rule. If we do it, we're going to get 5x to the 4th on top, e to the x on bottom. They both go to infinity, so we use it again. I'll just use L for L'Hopital's rule. Then you're going to get what? The limit, as x goes to infinity, of 20x cubed all over e to the x. You can see we just keep doing it a couple more times. Well, let's just go ahead and do it. And you're going to get 60x squared over e to the x. Still have infinity over infinity, so you can use it again. Then you're going to get 120x over e to the x. Still both go to infinity. But now finally this time, when we do it yet one more time, we're going to get 120 on top, e to the x on the bottom, and now it's clear that this is staying the same, whereas this is getting big, so the ratio is going to 0. So that tells us not only that this thing is outgrowing x to the 5th, but you can see we could have used exactly the same, heck, live wild. You'd use the same thing for this. E to the x is going to eventually leave this one in the dust. This one will be ahead for quite a while, but as x goes to infinity, there it is right there. It's going to leave it in the dust. The ratio is going to go to 0, which means that this thing grows faster than any power of x, no matter how big, any fixed power. Well, since e to the x and ln of x are inverse functions, it seems reasonable that if this thing grows faster than any power of x, that is inverse. If this thing grows faster than, say, x to the 100th power, that the ln of x might grow slower than the inverse of this. The inverse of this is the 100th root of x. Okay, here's the 100th root of x, something like that. And so the point is, since this thing grows slower than e to the x, it seems reasonable that the inverse of this thing, namely ln of x, is going to grow slower than the inverse of this thing, namely that. Okay, let me prove it to you. Okay, let's prove it again. Here's L'Hopital's rule. If we use ln of x divided by the 100th root of x, that's the same as, use L'Hopital's rule here. Let me first be very clear here. They both are going off to infinity. That's when you can use it. So we use L'Hopital's rule. And as x goes to infinity, the derivative of the top is that. The derivative of the bottom is what? That's x to the 1/100th power. So if I take the derivative, it's going to be 1/100th x to the subtract 1 is going to be negative 99 over 100. And that is, I'm not doing any calculus now, I'm just doing algebra. You can bring the 1/100th up on top, comes up as 100. I can bring this x to the first power down and combine it with this one. It's going to be x to the 1/100th power. X to the 1/100th is the same as the 100th root of x. And as x goes to infinity, that thing goes to 0. So this gives us something very important. And this is something which applies not only to graphing functions, but becomes very important in Calc 2 as well. If you want to look at the rate at which things grow, as x goes to infinity, you'd have x here, then you'd have x cubed, x to the 100th, and then growing faster than any of these, you'd have 2 to the x, and then e to the x, 10 to the x, and then something grows faster even than that if you have x to the x. Then not only is this growing, but that's growing. So that's the rate at which they're growing very fast. If you go down in this direction, you have like the square root of x, the cube root of x, 100th root of x, then the ln of x. And if you want to grow even slower than the ln, shoot, I didn't leave enough room, you could have the ln of the ln of x. Okay, grows very, very slowly, because that grows slowly, and then you're taking the ln of that, so it grows very, very slowly. By the way, if you didn't have x's, if you had n's in here instead, where n stands for an integer, then you have the same thing, because n is just growing just like x is. But then there's one more kind of important one you can put in here when you're talking about integers. It's n factorial. Factorials show up a lot in math. It showed up just now when we had x to the 5th power, and after taking 5 derivatives, we had 5 times 4 times 3 times 2 times 1. That's the definition of 5 factorial. N factorial is just what you get by starting with n and going all the way down to 1, multiplying everything. Okay, so you're learning all sorts of stuff, which is good not only for now, but also for the future. So let me write down the final result, and let me be clear about something, that it doesn't even matter whether this x right here is going to infinity or not. As long as these things here are both going off to infinity, doesn't matter whether they're positive or negative, because a negative you could just bring out front. So the point is they're both getting arbitrarily big. Then, and this could be anything you want. Let's just put an a there. It could stand for 0 or 2 or infinity, minus infinity, whatever you want. But as long as this ratio is like this, then, according to Hopital's rule, all you have to do is take the derivative of each one and if that limit exists, then whatever that limit is, this limit is the same. These two L's stand for two different things. This stands for the limit, that stands for using Hopital's rule. Okay, and then as we just showed, if this limit is still of the form infinity over infinity, you use Hopital's rule again until if you finally get your L. So this is the first lecture on Hopital's rule. In the next lesson, going to show you it's even more powerful than this. It's very, very cool. Very good.